Simpson's rule and Athos rule. Could they be two peas in a pod? Let's find out. Remember Athos rule? My student Athos thought that it would be good to approximate an integral by taking the average of the left endpoint and right endpoint approximations. Now, why would that be? Athos was motivated to propose his rule by observing a pattern that we have also noticed. And that's that the left endpoint and right endpoint errors are roughly the same sign, or roughly the same size, but opposite in sign. We can see that in tables of data that we looked at. And there is verification. There's kind of confirmation of that to some extent in the error bounds. The error bounds for the left endpoint and right endpoint approximations are the same. And indeed, you can show by thinking about whether your function is increasing or decreasing on a given interval that the left and right endpoint approximations are pretty much always going to have opposite signs in their errors. So there's a lot to be said for this. And what we can also say then is that hey, we could average these, and if we did so, these opposite and almost equal errors would pretty much cancel out. And so the thinking is that that's why averaging them should give a much more accurate approximation. So, and it turns out that that's right. Okay, so that seems revolutionary, and seems like, hey, maybe Athos should be famous for that. But then we get a little bit of a letdown perhaps for Athos, and an interesting twist for us. It turns out that Athos rule, which was developed kind of from numerical considerations of, hey, we want to get these errors to cancel out, is the same as the trapezoidal rule. Trapezoidal rule that was developed for geometric reasons. The idea that, hey, let's use something besides a flat, horizontal line segment for the top of our subinterval approximations. But it turns out that these two rules that come from sort of different motivations, different developments and rationales, they turn out to be the same thing, as we saw. The trapezoidal approximation with n subintervals will always equal the average of the left and right endpoint approximations with n subintervals. That's pretty incredible, pretty cool how that turns out. Now, that might get you thinking. Could we do something similar? Could we reason similarly to Athos and develop a super accurate approximation using the midpoint and trapezoidal rules? Because we have also seen from the data, let's take a look at that, that the trapezoidal approximation is roughly twice as far off as the midpoint approximation, but in the opposite direction. Now, granted, we just based that on, observing some numerical results. We saw it here in this example. But once again, it turns out this is not just a fluke. This is what typically happens. So the error bounds, once again, lend some credibility to the idea that this happens, because we see that the midpoint error bound is exactly half that of the trapezoidal error bound. And in fact, you can justify, I think this is an exercise in our textbook, that the midpoint and trapezoidal rules will be off in opposite directions. As long as you've got enough subintervals and there's nothing really weird happening within each subintervals, it really makes sense that they are going to be off in opposite directions. Okay, so how do we average them? It would not make sense to average them exactly because they aren't approximately equal. One is approximately equal to the double of the other. And so what we should do is use a weighted average. We need to do that in order to get these errors to roughly cancel out. Okay, so we should double the midpoint approximation, okay, to kind of double its error, so to, double its error too if you doubled it. And then add that to the trapezoidal approximation, which will now be approximately equal in magnitude to that double and opposite. And then we'd have to divide, and this time we're going to be dividing by 3 since we're averaging two things. The midpoint approximation is in there twice. And so the thinking goes that with the trapezoidal being twice as far off as the midpoint, this should now roughly cancel out and give us a super accurate approximation. And it does, once again. Sure enough, that weighted average of midpoint and trapezoidal approximations does give a much more accurate approximation in general than the trapezoidal and midpoint rules. Okay, but there's one more twist here. And maybe you expect it by now since we saw it before, but it does turn out that in fact S sub 2n is equal to our weighted average. That's right. The Simpson's rule approximation with two n subintervals. So we double the number of subintervals. We got to have it even for Simpson's anyway. It does equal our weighted approximation of the midpoint and trapezoidal approximations with n subintervals. Okay, so we see it here again at work. Even though the rationale behind Simpson's rule is geometric, approximating the upper boundary of each strip or the outer boundary with parabolas, curved things instead of with straight lines. It does turn out that the Simpson's approximation can be expressed algebraically as a fairly simple combination of two of our other approximations. We're not going to go into why that's true. It's relatively complicated. Okay, but one neat thing about this is that, this is an alternative that you can use to compute Simpson's rule approximations. Yeah, you can use the 1, 4, 2, 4, 2, 4 kind of thing as well. That's all well and good. But especially if you are already computing midpoint and trapezoidal approximations, hey, you can just use those results to get a Simpson's approximation. I guess one thing that would be tricky is it might not be the same number of subintervals. I hadn't thought about that till just now, but that discrepancy might make it a little harder to use this. So be cautious about that. But once again, it's kind of interesting how, Athos had this idea, and of course he's not known except to us here as having any fame for coming up with this idea. Simpson, on the other hand, has got quite a bit of fame. He's in all the calculus textbooks and so on, even though he wasn't the first one to come up with Simpson's rule. But it's just kind of interesting, the twists of fate and history and so on that lead to some people becoming famous and not others. Because once again, we do have two very similar flavors here in terms of Simpson's rule and it relating to others, as with the trapezoidal relating to two of our others as well. So I think that's interesting. I think it's a cool connection between more of our rules, and hope you enjoyed it as well. All right, see you soon.